Ngalakin kadijan nyunga boja.
Hello everyone, welcome to the lecture in week 2. In this week, we are going to keep discussing the chapter 1. So we call that as chapter 2 of the random variable. In our class in week 1, we discussed single random variable cases, including how to define a single random variable, some tools which can be used to analyze or fully describe a random variable. And we also introduced something like the function of random variable and also 6 types of distributions. So 3 continuous cases, 3 discrete cases. And in the part 2 today, we are going to keep the topic, but we are going to introduce some complicated cases. In last week, our discussion focused on the single random variable case. And in this week, we are going to extend from a single random variable to multiple random variables. And I want to divide our class into 2 parts today. The first part will focus on the cases where we have 2 random variables involved. And in the second half, so we are going to put a number of random variables into a group, or in other words, in a vector. Then, based on this group or vector of random variables, we are going to discuss their features, their properties, or something like that. Okay, now let's start the first part. If we have 2 random variables in our system, so how to analyze the features, the behaviors, and the properties of them? Okay, at the very beginning, same as last time, we are going to introduce some important so-called tools which can be used to analyze the pair of random variables. The first concept introduced in this part is called joint CDF function. The CDF term remains the same as the single random variable case, which stands for the cumulative distribution function. But why do we call that as a joint CDF function? That is because you have 2 random variables, for example, x and y, are involved in our discussion. And this CDF function is used to describe the joint behavior of these 2 random variables. So we call that as the joint cumulative distribution function. For such joint CDF function, the notation remains the same. We still use the capital F to denote this function. Next to the capital F, the x and the y are used to denote the names of the 2 random variables involved in this evaluation. And then the lower x and the lower y in the round brackets are just the parameters. The lower x is for the random variable capital X. The lower y is for the random variable capital Y. Okay, this is a notation used for the joint CDF. The definition of the joint CDF also remains the same or similar to the single random variable case. So last week we introduced for a single random variable x, for example, is CDF cumulative distribution function is defined as the probability that the value of this random variable is smaller or equal to the lower x. Now, for the 2 random variables cases, so we say we have the x random variable and the y random variable. The definition is similar. So we define the joint CDF f, x, y, x, and y equals another probability of you want. But in this case, because we have two random variables involved, so this will be a joint probability. Or in other words, the probability evaluation for a joint event. The first event will be the value of the random variable x is smaller or equal to the given parameter x. And the second event is the y random variable is smaller or equal to the given parameter lower y here. So that means, again, the joint CDF is evaluated as a joint probabilities. Okay, and because we said the joint CDF is actually a probability, so we can say the value of the joint probability must be smaller or equal to 1 and also greater or equal to 0. In other words, 0 and 1 should be the minimum and the maximum possible values for a joint probability. This remains same as the property for the general CDF function for single random variable. Okay, and what is the physical meaning of the joint CDF? So that was given in this section. But from our definition, we can observe this physical meaning directly. The joint CDF of the x and y for the given pair of parameter lower x and lower y is actually the probability that the random variable capital X is smaller or equal to the given parameter lower x, and in the meantime, the y random variable value is smaller or equal to the given parameter y. These two so-called events, this one and this one, happens at the same time. So it's called joint probability, right? And we must also notice for joint CDF function, because we have two random variables plus the joint CDF function itself, these three parameters comprise a three-dimensional space. So in the graph shown on the right-hand side of the slide, we have two graphs. So let's focus on the first case, the one on top, which is for the continuous random variables x and y. So we can see this is not a curve actually. This is a surface. This surface is the joint CDF surface in this case. It's not in a two-dimensional space anymore. We are coming into a three-dimensional space. The random variable x and the random variable y construct the xy plane, and the joint CDF function is the third axis going up vertically. So this is a three-dimensional space, and our CDF function curve or surface is defined within this three-dimensional space. For discrete random variables cases, it's the same. The only difference is that the shape of the surface of the cumulative distribution function for discrete random variables x and y are not smoothly going up. It becomes so-called stepwise style. This is just totally because we got discrete impulses, discrete probabilities when x and y values are defined for the discrete random variable cases. Okay. Okay, this is the main features regarding the joint CDF. There's another important properties, which is now given in the slide, but remains the same as to what we introduced in the single random variable case. Can you recall in the single random variable case is that all the CDF function must be non-decreasing function. So this feature remains to be true in the two random variable cases. So you can see when we, so for example, in the first graph in the slide, when we increase the x value and the y value, see here, this is the origin, and we will increase the x value and increase the y value here. So the value of the joint CDF surface is always going up or stay the same, but never goes down. This is true because the joint CDF function is accumulating the past probabilities of the x and the y, these things. So can just go up or stay the same, but never goes down. Okay, easy stuff. And for the discrete random variable cases, the joint CDF is also holding this property. So staying the same or going up, but never goes down. You can see when the x is going up or y is going up, so the steps remain same or jump to the next higher step, but never go down to next lower steps. Okay, so this is just about the features of the joint CDF function. Before moving on to the next slide, we got a small question. We want you to consider if such a joint probability is equal to the product of these two separate probabilities. For such question, actually, this is related to the joint CDF. So in this question here, let's just use the space to write it, okay? We are evaluating the joint probability of x smaller or equal to the lower x, and the y variable is lower or equal to the given parameter lower y here. We should understand this is actually our joint CDF function for x and y, okay? And how to solve this question? Actually, this thing, the joint probability can be translated or solved by using what we have learned called Bayes' theorem to the product between the conditional probability with another probabilities, which is equal to p x smaller or equal to x conditioned on y smaller or equal to lower y multiple the probability of the condition, which is y is smaller or equal to the lower y. And actually, this product is conducted between a conditional probability with the probability of condition. Question is asking, is this one equal to the probability of the x smaller than the lower x multiple the probability of y smaller or equal to y? Actually, this term by this term is equal to this first term is actually the CDF function of the x random variable itself, and the second term is the CDF function of y random variable itself. The original question is asking if this one equals fxx by fy y or not. Generally, answer is no. Again, this no is just for general cases. Okay, in some exceptions, the answer may be yes. We are going to talk about that later. But generally, they say no. The reason we say no is if you compare between these two steps, okay, this part and this part are the same, no problem at all. But the first term between the two parts of the equation are generally not equal. The first term here given on the left hand side is a conditional probability, and the second term given here is just the probability of the x smaller or equal to x event. This may not be the same. Generally, they are not equal. So in other words, generally, these two things are not equal. We can see exceptions very soon. Okay. Now this is regarding the introduction of the joint CDF. Let's move on to the next part. So what is joint PDF? Again, let's recall what we have learned from the week 1 lecture. For the single random variable cases, if you have already known what is the CDF function for this random variable x, so the PDF of the x is the fxx equals the derivative or differentiation of the corresponding CDF function with respect to the x. This is for the single random variable case. Now we are moving on to the two random variables cases. The idea is the same. Notation for joint PDF is also lower f, but this time we have two random variables involved, so x and y. So we need two parameters, lower x and lower y. And then this joint PDF is also used to measure the change rate of the corresponding joint CDF. But you have two random variables. So when you evaluate this change rate, you have to evaluate the change rate for each of the two random variables, respectively. So let's do the first one. We want to evaluate the change rate of the joint CDF with respect to the x. So we just put f, of course, it is joint CDF. So fxy and xy. Now, how to evaluate the change rate of it with respect to x only? So we are using a partial derivative with respect to the x. And after this step, we repeat the same procedure for the other random variable y. So we do the partial derivative to the y again. But this time, this is the second time we do the partial derivative. So second order of that. This is how we calculate the joint PDF from the joint CDF. We just repeat the partial derivative to the joint CDF 2 times, one for x, one for y. Then we got that. And this for the continuous random variable cases. If you got discrete cases, it will be much easier. We just need to evaluate what is the probability when the random variable x equal to xi, and what is the and in the same time, what is the probability that the y random variable equal to the yi, something like that, is the evaluation of the joint probability. Okay, so you can see here, this pik is actually the joint probability that the x equal to xy, x equal to xi, y equal to yk, this whole thing. Okay. So on the right hand side of the slide, you can see the two examples given in the graphs. The first case is the PDF, the joint PDF for continuous random variables. And this is x direction, for example. This is the y direction. And similar to the joint CDF, the joint PDF is also in a 3-dimensional world. The random variable x and the random variable y defines the xy 2-dimensional space, and then the value of the joint PDF is the vertical axis. So because you have 3 factors here, x, y, and joint PDF, so this surface is within a 3-dimensional space. And this surface is a continuous surface for continuous random variables. At the bottom, the second graph is showing you the discrete random variables cases. So same thing, x is given here and y is given here, but in this case, x and y, these two random variables, are discrete. And at a particular point, so I zoom in a bit. For example, if we talk about that blue small segment, so we say x 1 is getting here, and y1 is getting here, just two discrete points on the x and the y x-axis respectively. And this x1, y1 is defining a point. This point is x equals x1 and y equal to y1. So this is just a point. At this given point, the height of that small blue column is indicating the so the height of this small blue column is indicating the probability that x equals x1, y random variable equal to y1. For the green and the right small columns, the idea are the same, but we just need to change the index numbers of the x and the y, these two values, to maybe x2, y2, x3, y3, just indicating different points. Okay, this is just about the joint PDF, and very fundamental and easy to understand. Sorry, one. So I have to reverse back. Just one more thing I want to remind you, and we have known. So there are two cases. One is continuous random variables case. The other one is discrete random variables cases. It's very easy. In the discrete random variable cases, that the height of each single impulse is indicating the corresponding probabilities. Okay, but in the continuous case, can we say fxy x1 y1? Okay, for example, we say x1 here, y1 here. So these 2 points, these 2 values defines a node here, and at this node we go up. Okay, we find this is just height of fxy x1 y1. Can we say this joint PDF is indicating the probability that x equals x1 and y equal to y1? Is this true? Answer is no. Because for continuous case, as we discussed in the single random variable case, the height of the single position doesn't mean the probability. But how can we evaluate the probability that So how can we evaluate the probability that x equals xi and y equal to yi for continuous random variables? So this can be evaluated by fxy xy. So this is joined the PDF at the particular point xi and yi by dx dy. Okay, in our discussion in last week, we have already mentioned this one, and we used some example to tell you the reason. Remember that the velocity and the displacement of the small box, that's the same reason. Okay. After understanding the concepts of the joint CDF and joint PDF, we are going to keep introducing some properties regarding these 2 concepts. The first concept is to analyze or calculate the probability that the value of x and y, these 2 random variables, fall into the small region D. At the bottom of the slide, on the left-hand side, you can see our first graph, and this 2-dimensional space is defined by the x and y, these two random variables. And in this two-dimensional space, we define a small red color square region. We call that as region D. So we want to evaluate the probability that the x and y value fall into this small region D. In other words, when you evaluate this probability, you are evaluating that the x random variable, so here's the x random variable, is within x1 to x2 region. And also, the random variable y is in between y1 and y2 region, so within this region. If the x and y can satisfy these two conditions all at once, we can guarantee the point defined by the x and y are within this red color square region D here. Okay, this is just an idea of the equation. And how can we solve that? So what we are going to do is to divide this region D into many small grids or smashes. And each small square is called subregion DI. So that is defined here, okay? So DI is just one single element within the region D. How many subregions do we have? Many. So for each single subregion is small enough to use the D to denote it. For each single square here, DI, its dimension is dx by dy. In other words, horizontally, dx, vertically, dy. And image the dx and dy are all approaching to 0, very tiny one. This question is asking us to evaluate what is the probability that x and y fall into the region D. This is translated to the probability that x and y value fall into the first small subregion D1. That means, okay, the first tiny point. Or, so we use plus for or, okay? That x and y fall into the second subregion. Or, again, until the probability that x and y is in the DI region, and so on. So we are going to repeat this procedure for all the small squares. The summation of all such small events gave us the total probability that the x and y fall into the big red color region, capital D. Or if you want to just use the compact format for this calculation, that's equal to summation, that's the probability x, y fall into the DI region for all the possible i's. Okay, this is how we understand this idea. In the next slide, we are going to see how we calculate this. Okay, let's have a look here. In this graph, in this slide, I'm putting 3 graphs in. The first one is our joint PDF between x and y. So that has been viewed in our previous slide, so it should be easy one. And in this part, I'm dividing the xy plane into many small squares. And I focus on a particular square here. Oops. So here, for this particular blue color square, so this size and this size is just dx and dy. In other words, by using the dx and dy, I'm picking up a small subregion. You can call that as di, for example. And what is the probability that x and y fall into this small di region? That's equal to the joint PDF at this xi, yi multiple dx and dy. The dx and dy is defining the area of this small square, or in other words, the area of the subregion di, and multiple the corresponding joint PDF. You are actually calculating the volume of this column. The volume of this column is indicating what is the probability that x and y fall into this small di region. And because the dx and dy are all very small, approaching to 0. So we can assume within the di region, the value of the joint PDF is a constant. So in other words, we do not need to consider the very sharp and varying value of the joint PDF within this small region di. We can assume is a constant within the di region, so that we can just make this calculation much easier. Okay, in this slide, we just need to understand that if you want to evaluate what is the probability that x and y fall into a small subregion di, we just need to use the joint PDF multiple dx multiple dy. Okay, so if you want to understand this idea graphically, we can see the volume of a column defined by fxy, xy, the joint PDF, the height of that, dx and dy is indicating the probability that xy fall into the di region. This is used to calculate a small sub-region probability. So this is the volume of that small blue column. But we mentioned for this big area, capital D here, it contains many small sub-regions, di. So we just need to do the double integration to count all these sub-region columns and put them all together. The result is the probability that x and y fall into that big red color region, capital D. Moving on to next part, the second property. In this part, we want to make the connection between the joint CDF and joint PDF. Of course, the result is very easy to be derived because this comes from the definition of the joint PDF. Just make maybe 1 or 2 steps conversion. But we want you to understand graphically what does it mean between the two different graphs. Okay, so let's just solve this or derive this one from the mathematical induction. From our introduction, the joint PDF, so F, so I use black pen anyway. The joint PDF is the double partial derivative of the corresponding CDF function with respect to the x and the y respectively. And if we move this term to the left-hand side, so we have the double partial derivative of the CDF equals the joint PDF multiple this term. And then we can do the double integration on both sides. So in other words, the left-hand side can be simplified to fxy xy. Right-hand side, so let's do some conversion. Double integration doesn't change. The joint PDF doesn't change, not necessary to change. But regarding this partial x, partial y here, normally we need to change notation to a dx and dy within the integration. And regarding the boundaries of the integration, because we are evaluating the CDF, of the function. So the lower boundary for both integration should be starting from negative infinity, and then to given the x value to given the y value, like that. So this relationship comes from the definition of the joint PDF. So it's why I said deriving this one should be easy mathematically. But how to understand the physical meaning of this formula? So we can use the graph given at the bottom to define it. So our formula can be divided into two parts, part 1, part 2. So the left-hand side one is the CDF function, or joint CDF function, for this one. The right-hand side one is the double integration of the joint PDF. The joint PDF is given here. Let's have a look at the relationship between each other. On the left-hand side one, regarding the joint CDF, this fxy, xy is just indicating a single value of the joint CDF at the given point, x and y. So if we zoom in here, let's assume this point is so-called x, which is this x. And this point is the y, which is given parameter y here. Based on this given x and given y, you are determining a point here. So we call that as x and y point. So starting from this point, going up, and on the surface, you can find the fxy point. This point is indicating our joint CDF. The height of this point is the value of this joint CDF at this given point defined by the lower x and the lower y. Okay, now bear that in your mind. On the left-hand side, we are getting a single point, and this single point is giving us a small height. Like that. On the right-hand side, what we are doing is calculating the volume of the small column. This small column is defined by the joint PDF by du by dv. Du dv are just two dimensions of the small subdivision subregion, and multiple the height. So this term here is telling us the volume of a single small column at the point defined by u and v. And then by conducting the double integration, we are considering all the columns defined from negative infinity up to x and from negative infinity up to y. So in this graph, you can see here, let's just assume this is x direction, and that is our y direction, and our so-called x point, y point remain the same. So this is the x, this is the y. So this point is x and the y here. So the right-hand side of the equation is actually calculating the sum of the volume of all these blue color columns from negative infinity to the given x and negative infinity to the given y here. And we are adding up all this volume of the columns together to get the corresponding joint CDF value. Okay, for that. So this is the relationship between these two terms. Okay. Okay, let's move on to the next part. I think this may be the very last property regarding the joint CDF and joint PDF. This idea is easy. This is the property itself, and you can see the left-hand side is similar to what we have discussed before, the double integration, the joint PDF, multiple dx, dy. The only difference is we are changing the upper boundary of the two integrations to positive infinity, positive infinity. Of course, the lower boundaries remain same, so negative infinity, negative infinity. Actually, this left-hand side of the equation is calculating the joint probability that x and y are falling into region D covering the whole xy plane. In other words, recall that small graph I showed you. So this x1, x2, y1, and y2. So they are defining red color region D here, right? So this is the one we discussed before, right? But so far, the x1 is changed to negative infinity, x2 changed to positive infinity, y1 is changed to negative infinity, y2 is changed to positive infinity. So after adopting these values, so this red color region D is extended to the whole x1 plane everywhere. Now the question is asking, actually this calculation is asking us to evaluate what is the probability that the x and the y value fall into this whole plane. Of course, the result is 100%, which is 1. Or in other words, this left-hand side is evaluating the total volume of all the possible columns within the xy plane here. You can see, compare this one with the previous one. That column, the small columns, covers the full range of the x and y plane here. Okay, and in the joint CDF, this probability is corresponding to the maximum value 1. Remember we mentioned the joint CDF is also a probability. Its maximum value is 1. Yes, this is the case. So we can just do one more step to make us clear on this concept. So equal to 1, what's 1? 1 is actually the evaluation of the f xy, the joint CDF of positive infinity to negative infinity, which is actually equal to the probability that the x, my fault, I think I can just write it more clear. So the probability, the joint probability that the x random variable value is falling into negative infinity to positive infinity, and the y random variable value is between negative infinity to positive infinity case. Of course, for these two formulas, the result, the numerical value is 1. It's 100% true. Okay. Marginal PDF. Marginal distribution of a subset of random variables is the probability of the random variables contained in the subset. It gives the distribution of the random variables in the subset without reference to the values of other variables. I think this is a general description to the marginal PDF. In our discussion today regarding the cases with two random variable cases, and the set of the random variables will be just x and y. This is just a full set of the random variables we have, and this is called the subset of the random variable. Is just x or the y. The marginal distribution of x, for example, is the probability of the random variables contained in the subset. So this part is x, for example. So that means the marginal distribution of x is the probability of x. It gives the distribution of the x in the subset of the x without referencing to y. Okay, actually, if you read this part, you can just make the whole thing much more clear. In this system, we have two random variables, x and y. This is a whole set of the random variables in our system. We want to evaluate not the full thing. We want to focus on x only, for example. So we are evaluating, for example, PDF of the X. So this is not really called PDF. This is called marginal PDF because we are ignoring the Y here, right? So this is called the marginal distribution of X without referencing to the value of Y. So you can see here in this evaluation, we don't have the term Y because we are not referencing to it. Okay, so this is the idea of the marginal PDF of the two random variables case. Calculation, pretty easy. So there are two different cases. For continuous case, please use this formula. For discrete case, please use such formula. But how to understand that? So let's use some simple example to expand this formula, okay? So the marginal PDF of X is denoted by this one. Is equal to, if you got continuous random variables, you got integration from negative infinity to positive infinity with respect to the other random variable, which is Y in this case. And inside of the integration, we just need to put our joint PDF inside. How to understand this in here? So let me use a small graph to show you here. In this case, we have to plot our joint PDF. Sorry guys, again, I'm not good at drawing, so I will try my best to make the drawing clear. But if I failed, please let me know. I can give you more explanations. Okay. Now, I assume I know the surface of this joint PDF, which looks like, let me change the color maybe, it's in gray color. Maybe something like this. And also this is surface, right? So maybe like this. I'm not sure if you can understand what I'm drawing. I'm trying to just sketch the surface, okay? The surface of the joint, PDF between the X and the Y. Now, what you are going to do here is to evaluate the marginal PDF of the X only. Now let's make the whole question easier. We assume temporally X equal to X1. So X1 is a value given here. So in other words, I want to know what is the marginal PDF value at the given point X1. So on the right hand side, of course, you can see the X1 equal to the integration of X, the joint PDF, and X1 and Y, then dy. Because you have already point or fixed a point X1 here, so X1 doesn't change temporarily. So we just draw this reference line. So this is X1 line. So X equal to X1 line. On the right hand side, we are doing two things. First of all, we are calculating this product between the joint PDF with dy. The second step is to do the integration with respect to y. Okay, we pick up a small y dy here. We assume this is a small dy. So at the given point x1, we want to calculate the dy multiple the joint PDF. So at this given x1, the dy is given here, right? So this dy. We want to use dy to multiple the joint PDF. Okay, at this particular point, the joint PDF is given. Let me just draw it out. Okay, this height is the f, x, y, x, and y. The height of the PDF, joint PDF, at this given particular point, right? And when you use dy to multiple this, the height of the joint PDF, actually you are calculating you are calculating the area of this small column or rectangular shape. So the area of that, okay, for small dy region. But here, the next step, we are going to do the integration from negative infinity to the positive infinity of the y-axis. That means you have to repeat this procedure for next dy. So next small dy, and again, to the other side, same thing. Yeah, repeating these procedures, repeating this procedure. So after you finish the calculation of this stuff, actually the result of this integration is the total area of this curve. I know it's a little massive, but I hope you can understand that, right? This curve is the curve of the joint PDF when the random variable x equal to x1. And this integration at this x1 point is returning us the total area of this shadowed section. In other words, the marginal PDF at a particular point x1 is the area of the corresponding curve in the joint PDF. Okay, of course, we'll change the x1 to another point. For example, if you change to x2, so you will have another function curve, maybe something maybe like this. And then again, you need to evaluate the area of this green color shadow section. And that area is returned back to be the value of the marginal PDF at the given point x2. So this is what happened. So what we can do here is to use this way to eliminate the effect of the random variable y, and the remaining thing is just the marginal PDF of the x only. Okay, so this is just how we do this calculation, or how to understand this thing. For the discrete case, what we have discussed here are related to the continuous case. But for the discrete case, the things will be much easier, okay? Very similar. So we just got our x, y, and the joint PMF here. So at some particular point, for example, x1, x2, x3, y1, y2, and y3. So because we got discrete random variables x and y, so at discrete point, we may have some impulses in the joint PMF. For example, at x1, y2 this point, so this x1 and y2 point, you got one single impulse. The height of this impulse is indicating the joint probability that x random variable equal to x1 and y random variable equal to y2. Okay, something like that. And at x1, y1 point, you got another impulse. At x1, y3 point, you got another impulse, or something like that. You may have others, like maybe here one, maybe here one. It's just example, okay? Now, if you want to evaluate the marginal PMF, so we are going to, so let's just use the same notation, okay? So we say we want to evaluate fx at x1, for example. So regarding this point, that's equal to actually summation of the probability that x equal to x1. This doesn't change because you focus on x1 point, for example, and y, capital Y, equal to yi, I equal to 1, 2, 3 in our example. This is equal to the summation of all the joint probabilities. So x equal to x1, y equal to y1, plus x equal to x1, y equal to y2, plus x equal to x1, y equal to y3, because we have only 3 impulses in this example, so we just stop here. Okay, so that means for this given x1 point, we focus on all the impulses along this line here. In this example, there are 3 impulses at x1, y1, x1, y2, and x1, y3. So we just need to add up all 3 impulses. The summation of them should be the marginal PMF at the x1 point. Of course, if you change that to the x2, x3, you can repeat the same procedures to derive the corresponding values. After you evaluate all the possible x values, you finish the evaluation of this marginal PMF of x function. Okay, so this is the idea of the marginal PDF or marginal PMF. We just want to use this way to eliminate one random variable from the joint one, so that we can get the distribution of one particular random variable without reference to another one. Okay. Okay, now let's move on to stay in the same slide, and there's a small thing left. So at the bottom of the slide, we can see if the events are independent, then we have that relationship. This joint probability equal to the product of 2 separate probability. This thing has been mentioned in our first slide discussion. In that slide, we said generally we answer no, this relationship doesn't exist. But why we say they are possible in this case? The only reason is we have one more condition. The condition is saying the 2 random variables are independent between each other. So everyone please be reminded. This is called the independent relationship. Is very important for our future study. So I want you guys to understand what does independency mean here. If we say the random variable x is independent from the random variable y, so that means the x and the y are totally separate and no relationship at all. No any relationship. No matter what happened on x, it will not affect y. Or in other words, no matter what happened on y, it will not affect x. Maybe we can use a simple analog example to help you to understand this thing. We say we have 2 events, not random variables, okay? Just events. Event A is the color of my shirt on one day, maybe today, whatever. The B is what did you eat in the breakfast? Okay, these 2 events. Are these 2 things related between each other? So in other words, if you know something about event B, can you get some information regarding A? Or if you see the event of A, can you know what happened on B? So of course, in this example I gave here, no. For example, okay, maybe in my event B, in my breakfast, I ate 1 sandwich. From this thing, can I determine what color of my shirt? Of course not. So in other words, today when I come to my class, I'm dressing maybe a white color shirt. From this information, do you know what breakfast did I eat? No, no way to know that. So this A and B, these 2 things are totally separate. If the A and B, these 2 things are totally separate, or in other words, independent between each other, so I want to ask, what is the probability that A event happen subject to B? So here A and B are independent between each other. So this conditional probability is saying, if I give you the condition of B, for example, you are eating a sandwich, what is the probability of A, for example, dressing a white shirt? But these two things has no relationship at all. Knowing B or not knowing B cannot affect evaluation of the probability of A. So this is equal to the A if A and B are independent. Sorry, it's too small. Are independent. Okay, so now we are going to use this so-called knowledge or whatever information to derive this joint CDF information. Okay, so first of all, the joint CDF fxy xy, based on the definition of it, should be equal to a joint probability that x is smaller or equal to the lower x and the y is smaller or equal to the lower y. This is the joint probability. As we mentioned in the first slide, by using Bayes' theorem, this is equal to a conditional probability multiple the probability of the condition. But now we have a new condition that x and y are independent between each other. Because x and y are independent, so such conditional probability is just equal to the probability of the event A. Similar, this is equal to this if x and y are independent between each other. Okay, and then we copy the remaining thing, y smaller than y. This and this are just the definition of the CDF function for each of these two random variables. So this is equal to f x x, that is f y y. Okay, now we derive what we want. Such relationship is holding only when the x and the y are independent. Okay, that's that. Another similar result can be derived by using the same way. I leave that to you guys. By finishing this slide, we have already known actually, if x and y are independent, the joint CDF or joint PDF are equal to the product of the separate CDFs or separate PDFs of the two variables. Firstwise, if you can derive such mathematical relationships, you can also say these two random variables are independent between each other. Okay. Conditional PDF. I think this part is very similar as the one we discussed in the lecture 1. I don't want to just go through the mathematical induction again, so I leave that to you guys. If you do not want to just go through the mathematical procedure to understand, to derive this formula, that's fine, but you must know this formula. And you must understand the meanings behind them. Okay. Next one, expectation of a function g, and g function are using the random variables x and y as the parameter. So how to calculate the expectation of the g function? So in last week we have mentioned the expectation operation to whatever. So we put the x here. So actually anything will be fine. So the expectation operation is actually one integration to whatever you have in this operator. So we put the x here, for example, and then multiple the PDF of the random variable, then from negative infinity to positive infinity, like that. So we learned this one from last week. We also mentioned the expectation operation is just like a template. So you have the integration thing and multiple the PDF and DX thing. So no matter what you have here, try to put the same thing here. Get that? When we move on to this expression of the g function, which involves two random variables cases, the idea remains exact same. You can see the expression operation is also the integration by the PDF and dx dy. So it's still in the template. But because there are two random variables, so the integration will be a double integration. And the PDF will be replaced by the joint PDF. And then no matter what you have within the operator, you can use the same thing on the right hand side. Same thing. So very simple, right? Next concept is called the JL's moment. Moment has already been introduced in lecture 1. So we said for single random variable case, the moment equal to expression of the x power to n. Okay. For this double random variables case, the moment remains same. It's still using m to denote the moment. Why we call that as JL's moment? Because J and L are used to denote the order number of the two random variables, respectively. J is always the order number of the first random variable inside of the exclamation operation. And the L is used to denote the order number of the second random variable. Just that. And the remaining thing of the calculation of the exclamation are just simple. I skip that. Okay. And in this part, for the JL's moment, there's a special case you must know. When the J equal to 1 and L equal to 1, this JL's moment becomes the first order moment, and M11 equal to E multiplication of x power to 1 by y power to 1. Calculation is your homework. You can do that by yourself. Okay. So what I say, this thing is called correlation between the x and the y. And you don't need to worry about this one at this moment. And we are going to use a long time to discuss this issue. And this will be important concept for our chapter 2 study. So far, I just give you this idea to you. Normally, we are using capital R to denote it. Okay. And the next concept is the central moment. So JL's central moment. Last week, regarding the single random variable case, the nth order central moment is defined as the E expectation, random variable x minus the mean value of the x, then power to n. Okay, this is what I have learned in last week. And in this week, for the two random variables case, we are defining the JL's central moment. The idea remains the same, but you can see the JL's central moment is equal to the expression inside of expression, because you have two random variables. So you have two terms. First term for x, second term for y. And this J is the order number, or the power number of the first term, and L is for the second term. Each of the two terms will be x minus, x is just random variable value, right? X minus the mean value of the x. So this EX is the mean value of the x. EY is the mean value of the y. Got that? But we don't use the JL's central moment too much generally, except the one exception. When the J equal to 1 and L equal to 1, in this case, this CJL becomes C11 is actually the expression of x minus EX by y minus EY here. This calculation is very, very important, and you will use this one many, many times until the end of the whole semester. we call this as covariance. Okay, normally we use capital C or COV to denote it. So in next page, we are going to keep discussing this concept. But please remember, the covariance is a very special case for the central moment. So that means J equal to 1, the L equal to 1. Okay. So here, we started to discuss the covariance. Because the covariance is very important, so we have a very special dedicated notation for it. So capital C. Okay. And X and Y are used to denote this covariance is between the X and the Y, these two random variables. Sometimes we can use such kind of notation. So COV for covariance, and then brackets between X and Y to denote the same thing. So these two notations are the same with each other. Okay. And we have mentioned the covariance is calculated by using the first order central moment formula. So this is introduced in the first slide. I skipped that part, okay? But how can we derive the very last term here? So here, let's just quickly go through that. It said Cxy equal to the expectation of x minus Ex by y minus Ey here. Let's just expand the terms within the square brackets. So what we have is x by y is xy minus x by the ey, so x e y minus y by the ex plus ex e y here. Next step, because inside of the square brackets, we got just the summation or subtraction between different terms. So the expectation operator can be given to each of these four terms. So this is converted to expectation of the first term minus expectation of the second term minus expectation of y by ex plus finally the expectation of what? So ex e y thing here. Now before moving on to next step, so let's just examine these terms here. I want to draw your attention, everyone. So if we say x is or y is a random variable, the mean of the random variable will be the ex and ey, the expectation of them, right? For a given random variable, the expectation of it, or in other words, the mean of it, must be a constant. Must be a constant. The constant may be different between different random variables, but must be constant. Normally, we use mu to denote it. So mu x or mu y to denote the mean value of the random variable. Okay, so not important, but I just want you to know the expectation of a random variable must be a constant. And after knowing this in here, another two important property or properties regarding the expectation operation must be known. First one, the expectation of a constant is the constant itself. And the expectation of a constant C multiple a random variable is equal to C multiple the expectation of random variable. These properties have already been introduced last week. If you forgot it, please just review them. Okay. So now by using this preliminary knowledge, we are going to simplify our work. First term doesn't change. It is expectation of x and y. We can't simplify this one further. But in the second term here is equal to expectation of the random variable x multiple the mean of y. We have mentioned the mean of y random variable must be a constant, and the expectation of a constant by random variable is equal to this constant by the expectation of the random variable. So we can move the EY out because this is constant. Then we have only X left in the expectation operation. Do the same thing for the third term. We got the EX out and then have the Y left in the expectation. And then by the end, EX, EY are the means of the X and the Y respectively. And the expectation of these two constants are just the constants. In other words, the expectation operation cannot play any special effect to constants. Next step, we simplify the equation by cancel some general terms. For example, this term and this term have the same items inside but different signs, so we cancel these two. And then the result is changed to EX by Y minus EX EY. Okay, this is such result. Okay, before moving on, there's one more thing I want to remind you. So yes, I know how to calculate the covariance between an X and a Y. What's next? Okay, the covariance is used to measure the joint spread or variation of X and Y about the mean value of these two random variables. In the graph shown below in this slide, we can see here, for example, in the first graph, that is about the random variable X, and the mean value of this random variable X is this line. Of course, for the random variable itself, the values will be different time by time. For example, at the moment T1, we got the value of the X sample at X1, and the distance between the X1 value to the mean value of the X is this. In the meantime, regarding another random variable Y here, of course, the mean value of the Y is given here, and at the same time T1, the sample value Y1 has the distance to the mean value like this. If you compare these two samples, so X1, Y1, at the time T1, you can find both of these two distances are above the mean values of these two random variables. When we shift to T2 moment, okay, in this case, both samples X2 and Y2 are all below the mean value of these two random variables respectively. And go to the X3, so Y3, they are all above the mean value. So if you just compare the behavior of these two random variables, you can find they have some kind of similar moving trends or similar behaviors. So at a given time, both are higher than the mean value, or at the same time, both are lower than the mean value. So in such case, we can say the behavior of these two random variables are similar. Okay. So the covariance is used to measure such behaviors. Are they similar or opposite, or totally no relationship? Now let's just have a look at some details. Okay. Before that, before introducing the next example, let's give you the summary. And if you know summary, you can use this one to help you to understand the example next. Okay. Covariance measures the linear relationship. So everyone please highlight this sentence. So what does covariance do? It is used to measure the linear relationship between two random variables. If the covariance value is positive, so in other words, greater than 0, so that means these two random variables has a positive or similar linear behaviors between each other. If the covariance value is negative, that also means these two random variables has linear relationship between each other, but the behavior will be opposite with each other. So don't worry, we are going to see the example to understand this, okay? By the end, if the covariance value is equal to 0, that means these two random variables do not have linear relationships between each other. Okay, let's have a look at the example to see how to understand that. In this case, we have two random variables, x and y. Similar to the graph we've shown before, these two random variables' mean values are given here, so ex and ey. At different time instance, of course, you have different sample values. So x1, y1, x2, y2, x3, y3. So I want to observe the linear relationship in this case. So what we are going to do is, so let's focus on the x random variable first. So in the middle graph, I'm using the x as the horizontal axis and using the y as the vertical axis. And regarding these two random variables, the mean value of the x is at this position, and the mean value of the y is given here. You can see I'm using two gray color dashed line to indicate the positions of ex and ey, these two mean values. For the first pair of the samples, so x1 and y1, we can see x1 is higher than the mean value of x. So now along the horizontal axis, you can see I'm putting the x1 here. So x1 is higher than the mean value of the value of the x. And for the y1 sample, I do the same thing. So y1 is higher than the mean value of the y. y1 is higher than the mean value of y. Using this information, I'm able to put that x1 and y1, these two samples, on x and y, these two axes. And then this x1, y1, these two values can define a sample, which is called the sample at T1. By repeating this step, I'm able to plot another two samples at T2, at T3. So these three sample points are given as the blue dots in the third graph. And from this example, it seems I can use a linear line segment to connect these three blue points together. In other words, I'm able to use the red color line segment to describe the feature of the samples derived from these two random variables. Such kind of linear relationship is reflected by using a non-zero covariance, because we can observe the linear relationship between samples. So such linear relationship is indicated by non-zero covariance value. In this case, we can say the gradient of this linear line segment is positive. That is giving us the covariance between the x and y is positive, is greater than 0. Or in other words, the behavior of the two random variables will be similar between each other. That means if the x1 value, the sample x1 value is higher than the mean of the x, y1 is higher than the mean of y. If the x1 is lower than the mean of x, so the y will be lower than the mean of y again. You got high, I'm high. You got low, I'm low. So this behavior between x and y can be observed from such analysis. So such similar behavior is indicating that the covariance between x and y must be greater than 0, and it must be just positive, and the behaviors are similar. Okay. Another case, if the covariance between x and y is smaller than 0, is negative. In this graph, we can observe that when the x1 is high, at the same time, the y1 sample is lower than the average value of the y. But at T2, if the x2 sample is lower than the mean of x, y2 becomes higher than the mean value of y. And at the moment T3, this relationship is reversed again. You got high, I got low. So in other words, all the behaviors of the random variable y are just opposite to that of the random variable x. Of course, by using that procedure we described in the previous slide, we are able to plot all the sample points in the graph and use a line to make a connection between all the sample points. In this case, we can find this red color line segment is going down, which indicates a negative gradient. This negative gradient is also corresponding to a negative covariance value. The negative covariance value, of course, indicating the linear relationship, as you can see from graph. But the behavior between x and y are opposite between each other. Okay, this is the second case. In the third case, how about if the covariance value between x and y is equal to 0? Now, on the left-hand side, you can see the first graph. So x remains to be x, but for the y variable, the behavior is kind of really random. So if the x1 is higher than the mean of x, okay, y1 is higher than the mean of y. That's just kind of okay. But at the moment t2, x2 value becomes lower than the mean of the x. But for the random number y, the y2 value is still at higher than the mean value of y. It can't be understood easily, right? And when we move on to the time t3, so this time x3 go back to the value above the mean of x. But y3 go to the bottom, lower than the mean. In other words, from these two graphs, we are not able to really observe some kind of relationships between the values of x and y. And if you just use that method we introduced before and have a look at this graph here, yes, we can plot all three blue dots, the sample dots, but we are not able to use a linear line segment to link them together. And the line, the curve, which can connect these three blue dots together becomes a curve. And this is definitely not a linear thing. So that means we are not able to observe a linear relationship between x and y. This indicates the value of the covariance is approximately 0, very tiny. Okay, so now after we went through these three examples, we come back to our summary again. Covariance is used to measure the, okay, I just highlight this one, linear relationship between two random variables. If the covariance is 0, so we don't have the linear relationship between these x and y random variables. In the future, we are not going to use such a long term to say no linear relationship between x and y. So we want to use another professional term to describe it. We say x and y are uncorrelated. Now this uncorrelated means no linear relationship. Okay, and if the covariance cxy is non-zero, so that means between x and y, there is a linear relationship. So we call such relationship as correlation or correlated relationship. Okay, but regarding the correlation, there are two cases. So if the covariance is positive, that means the behavior of the x and the y are similar. So going up at the same time or going down at the same time, not opposite. But if the covariance value is negative, that means the behavior of the random variables are opposite each other. If x going up, y goes down. If x goes down, y going up, something like that. Okay. The covariance value ranges from negative infinity to positive infinity. Okay. And the magnitude of the covariance is not easy to interpret because it's not normalized. And as a result, depends on the magnitudes of the variables. Regarding the very last conclusion here, we want to use one more or two more slides to give you more explanations. Regarding the covariance, So we can judge the linear relationship between the random variables from only the signs of occurrence. So greater than 0, lower than 0, or equal to 0 only. So we focus on the signs of the occurrence, but we can't use the magnitude or the value of the occurrence to judge anything. Why we have this result? If the occurrence of xy equal to 5, doesn't it mean the linear relationship is much stronger than that of the case where the occurrence is equal to 1? Answer is no, it doesn't mean that at all. So let's see a quick example. Okay, the first one, actually we have mentioned the example in our previous discussion. We call that as case 1. In case 1, we have ex and ey, so x and y, two random variables. And based on this graph, we are able to evaluate the occurrence in this case is roughly 1.08. But in the case 2 here, in the case 2, I'm using same notations x and y, but actually the sample values are different. Okay. For example, just quickly, in the case 2 here, you can see this sample is pretty far away from the mean value of x. But for this case, this x1 sample is closer to the mean value. So the samples are different, actually. You can treat them to be two groups of random variables, whatever. Okay. So in the case 2, here, and we do the same thing to produce the graph. And based on the graph, we evaluate the occurrence of the second group of the random variables. Result is 4.48. In the first group, occurrence is 1. The second group, the occurrence is about 4.5. If you put these two groups of the random variables together to make a comparison, 1.08 for group 1, 4.48 for group 2. But graphically, these two linear line segments for these two cases are very close between each other. In other words, the linear relationship in these two groups of random variables are similar. That means a stronger or bigger occurrence value doesn't mean the linear relationship is stronger than the lower occurrence value. So here we say the value of the occurrence cannot be used to judge if the linear relationship is stronger or weaker. It doesn't mean that. So if you got only the occurrence values, you can only use the sign of the value to help you to judge if we got a similar behavior linearly, or opposite behavior linearly, or no linear relationship. Just these three cases, but you can't compare the values of them. But in some cases, we have to compare which group of random variables have stronger linear relationships. In such case, you have to normalize the occurrence values. But how to do that? Okay, in this calculation, we are introducing a new parameter called correlation coefficient, rho xy. Rho xy, the correlation coefficient, is a normalized occurrence. But how do we do that? So we are using the occurrence divided by the product of the so-called standard deviation of x and y. Remember how we define the variance of x? We call that a sigma x squared. The standard deviation is the square root of it, which is denoted by the sigma x. So this is called standard deviation of x. It's just square root of the variance of x. Okay, so doing this way. And some important properties regarding the correlation coefficient is, first of all, it's normalized, right? So the rho is normalized. So the rho xy value must be between 1 and -1. Now in this one, there are three cases. If rho x1 equal to the maximum value 1, this means very strong linear relationship between x and y. and the behavior of the x and y are similar because you got positive 1, okay? If the rho x1 equal to -1, that is also the strongest linear relationship. Oops. And this case, because you got negative value of the correlation coefficient, so the behavior of the x and y are opposite between each other. So you go up, I go to bottom. If you go to bottom, I go to up. Okay, this here. If the rho xy equal to 0, that means no linear relationship. So that is also indicating the cxy equal to 0. Okay, this is just about the correlation coefficient. Oops. Let's just have a look at what is the information. Okay, not too much. Okay, next one, some important properties. So the first one has been done. So if the covariance between the x and y is 0, then the two random variables are uncorrelated. That's okay. Next one, if x and y are independent. Okay, can you recall what is independency? Independency means these two random variables have no relationship at all. So no linear relationship, no second order, no third order, no any relationship. Okay. So if x and y are independent, so the exy equals ex by ey, so that should be easy. And finally, if the expectation of x by y is equal to 0, then we call the x and y are orthogonal. Regarding the orthogonal, in the third part of chapter 1, we have a section discussing the orthogonality principle. By then, we are going to review this concept again. Okay. Finally, independent random variables are uncorrelated, but uncorrelated random variable may not be independent. So actually, this concept or statement is talking about two sets of the relationships. The first set is the independent relation set, and the uncorrelated set is a bigger one. Uncorrelated. That means, okay, if we got one relationship here, this relationship, the green dot, is within the independent set. That means this green dot must be independent or independency. But because the independency set is the subset of the uncorrelated set, so this green dot must also means the random variables involved are uncorrelated. But if you got a dot at here, so this dot is not within the independent set. So that means the random variables involved in this right dot relationship are not independent. But in the meantime, this red dot is within the uncorrelated set. So these two random variables involved in this red dot are uncorrelated. So what I mean? Uncorrelated means they don't have linear relationship, but they may have the second order or third order or fourth order relationship. For example, y equals x squared. This is second order relationship, not a first order one, not a linear one. So that means this red dot may have higher order relationship if the x and y are uncorrelated. But if for that green dot here, regarding this green dot here, that has already been in the independent set. So the two random variables x and y involved in this relationship must be independent. So no relationship at all. Okay, that. Now let's move on to the next topic. So in the next two slides, we are going to study the conditional probability and expectation. In the current slide showing on the screen, there are four formulas. These four formulas can be divided into two groups. In the first group, this formula and this formula are used for discrete random variable cases, and the other two formulas are for the continuous cases. So our discussion now is temporarily focusing on the discrete random variable cases. And after we understand this thing, our understanding can be easily extended to the continuous cases. Okay, now let's start our discussion. Before our discussion, so I'd like to summarize what conditions do we have, or in other words, so what information has been given regarding this issue. So let's just write this down. So what has been given? There are three conditions are given in this question. First of all, there are two random variables which are called x and the y random variables. Of course, in this case, at the beginning of the discussion, we said these two random variables are all discrete random variables. First one. The second condition is a region A has been defined. A region A has been defined in the x and y plane. So the plane defined by the x and y, these two random variables. Thirdly, we have also defined an event, which is y falling into the region A defined above. Based on these three conditions, we want to determine, or we want to find the probability that y value in region A is in here. So let's just plot this thing out. So this is another three-dimensional thing, and horizontally we have the y and x, these two random variables, and these two random variables are creating a two-dimensional space. The third axis going up is the PMF, sorry, my fault, joint PMF or joint PDF. In this case, because x and y are all discrete, so here we are selecting joint PMF as the third axis. And the region A is defined within the x1 plane. So we just use a shadowed circle in the x1 plane to define the region A here. Now, the event that we are going to analyze is the y value is falling into A. If you really just focus on this particular term, y in A, so you can't see the term x. So the random variable x is not given, but the x is also playing an important role for this event. Let's have a quick look here. We pick up one value randomly, we call that as y1, for example. So at this y1 value, you can see some points in this segment or this segment are falling out of the region A. If you really want to have the point to be falling into region A, so you must select a good position for the corresponding x coordinate of the points. For example, I pick up x1 here. So x1 and the corresponding y1 will define a blue dot. This blue dot is currently falling into the region A. So this is a good one. But if you are selecting another node, another x direction, x coordinate, for example, x2 here, so x2 and y1 will give you a point out of the region A. Our target is to determine what is the probability that y in A. You still have to consider x, so that's important. Okay, now let's just clean the drawing, and we can just show you more details on this stuff. Okay, just 1 second. Okay, now how to evaluate this event. Because there are two random variables involved, so I'd like to finish this evaluation within 2 steps. In each of these 2 steps, I focus on one particular random variable. Okay, now let's have a look how to solve that. In the first one, step 1, I just want to temporarily focus on y. But for x, because we must use the x to help y to define a point, so that we can just say if the point is in or out of the region A. So for x, I temporarily fixed position of x. So here we call that as xi. It's just a general x value. Okay, so this xi value is temporarily fixed in the step 1, and based on this condition, so xi value is denoted by this dashed line. So here, for evaluating the probability of y in A, subject to the condition that the xi value has already been fixed for the random variable x. So we are putting this condition to this probability. Now this is changed to conditional probability. This conditional probability is equal to summation of the probability that y value, I mean the random variable y value, equal to yi when the x equals xi. In here, the yi is within the region A. That means, okay, let's keep drawing that. Along the y-axis, if there are 3 possible y values, say y1, y2, and y3. So xi value has been fixed as a condition. So by combining with the xi, so these 3 y values will give you 3 possible position of the points, which are at here, here, and here. Of course, in this example, only the xi and y2 giving you a point falling into the region A. The other 2 y values, y1, y3, are giving us the points out of the region A. So here, because the points defined by the y1 and y3 are out of the region A, so when you evaluate what is the probability that y in A, these 2 points do not need to be considered. In other words, we just need to consider the yi point, which can make the point within the region A with the x equal to xi condition. Okay, get that. Actually, in the lecture slides and also in your unit reader, so this long expression is shortened to be the format like summation, that's p probability, of course. So focus on the random variable y, and y step back to xi. This y is falling into the region A. This is the same meaning, so just make the whole notation easier, expression shortened. Okay, this is the first step. Now we have already evaluated. So if the x value is fixed, so what is the probability that y is falling into the region A? But actually, the x value is not fixed. So now we have to introduce the second step. Now we are going to observe the effect of different value of x. In this case, we are evaluating the final target. So what is the probability that y is falling into the region A? In this case, we just need to use what we have learned regarding calculating the joint probability by using the conditional probability from lecture 1. Okay, so because this current probability that y in A equal to our conditional one, multiple the probability that x equal to xi. Okay, I just want to write a small set of notes regarding this one. So what is this evaluating? This is evaluating the joint probability that y in A and x equal to xi. Okay, again, this is still focusing on one single point of xi. So what you need to do in this case is to add a summation sign. Once the summation sign is added regarding all the xi values for the random variable x, so we are going to go through all the possible values of x to add up such probabilities. The result is what we want. Okay. Now this is just how we solve this question to derive the total probability of an event, and this event depends on two random variables. We have said this is true for the discrete case, but how about if we got continuous case? Okay, continuous case is very similar to this one. Okay, if you got continuous case, the step 1 will be changed. So of course, the target is still to determine y in A, and then x equal to xi. So this part remains same as this part. But on the right hand side of the first step, because we got the continuous random variable, the y random variable is not discrete anymore, so we can't use such summation sign. We have used integration. And the next term, so the conditional probability will not be like that. Will be such conditional PDF. And then with respect to dy, and for all the y values within the A region. And the step 2 can be changed accordingly as well. So first thing is the left hand side, which remains unchanged. So still y in A, this probability, that's equal to, on the right hand side of step 2, the red color summation sign must be changed to the integration. And then this part remains same. We just copy that down. Y in A subject to x variable equal to xi. And be careful with the very last term here. So in the discrete case, that is the probability that random variable x equal to xi value. But because x becomes a continuous random variable in our current discussion, so this probability will be replaced by the fxx. This is marginal PDF of the x by the x. The x value is from negative infinity to positive infinity. Just that. Finish. Okay, so I think this part is not new because in our previous discussion we have talked about this one many times. So if the random variable is continuous, so at a particular point, the probability is equal to the marginal PDF or just the PDF by the small division, so dx. Okay, so this is what we discussed.